In this episode, we're going to make memory safety feel like a practical security topic rather than an abstract programming concern. Many brand new learners assume that software vulnerabilities are mostly about weak passwords or obvious misconfigurations, but a large portion of serious exploits come from memory safety problems, which are flaws in how programs handle memory. Memory safety issues can allow attackers to crash programs, steal sensitive data from memory, or even run their own code inside a program's process. The reason this matters for you, even if you never write code, is that memory safety flaws often sit inside widely used software components, and attackers can exploit them remotely through normal-looking data like network packets or file content. Understanding memory safety risk helps explain why updates are urgent, why some vulnerabilities are so high impact, and why certain mitigation techniques exist in modern systems. We'll focus on what memory safety problems are, how they lead to exploitation, what mitigations try to do, and why patching and updates are often the most reliable defense at scale. A good place to start is clarifying what memory is in a program and why it creates risk. When a program runs, it uses memory to store data it needs, such as variables, buffers that hold input, pointers that reference locations, and internal state that tracks what the program is doing. Memory is also where the program's instructions and control flow live while the program executes. Many programming languages and systems give programs direct control over memory for performance and flexibility, but that control comes with danger because mistakes in memory handling can cause the program to read or write outside the intended boundaries. Those boundary mistakes are the foundation of many memory safety vulnerabilities. Beginners sometimes think of memory as a harmless storage area, like a filing cabinet. But in software, memory is tightly linked to execution, meaning that corrupting memory can change what the program does. That's why memory safety flaws can lead to code execution, not just incorrect data. Once you see memory as both data and control, the severity of these bugs becomes easier to understand. One of the most common memory safety problems is the buffer overflow, which occurs when a program writes more data into a fixed-size memory area than it can hold. Imagine a container designed to hold a certain amount, but the program keeps pouring data in without checking size, causing data to spill into neighboring memory. That spill can overwrite other data the program uses, including values that control what the program does next. A buffer overflow can cause a crash, but attackers aim for more than crashing. They aim to control what gets overwritten so they can steer execution. Another common problem is reading beyond bounds, which can expose sensitive memory contents because the program accidentally includes memory it should not reveal. These are boundary errors, and they occur because the program incorrectly trusts input size or fails to validate it. For beginners, the key idea is that many memory safety flaws are fundamentally about missing or incorrect checks around how much data a program should accept or process. Another important category is use after free, which happens when a program continues to use a memory region after it has been freed, meaning it was returned to the system for reuse. This is like throwing away a piece of paper with a phone number on it, and then later reading from that same spot in the trash as if it still holds the original number. In computing, freed memory can be reused for something else, so a dangling reference can end up pointing to new data or to attacker-influenced data, which can lead to unintended behavior. Attackers can sometimes manipulate timing and allocation patterns so that when the program uses the freed memory, it contains attacker-controlled content that guides execution. Use after free bugs are particularly tricky because they can depend on complex program behavior and timing, making them difficult to detect and reproduce. For beginner learners, the takeaway is that memory safety is not only about size checks. It is also about life cycle, meaning whether the program knows which memory is valid and when. When a program loses track of memory life cycle, attackers can exploit that confusion. Memory safety problems can also lead to information disclosure, which is when a program leaks data it should keep secret. A program might accidentally send uninitialized memory to a user, revealing fragments of previous data, or it might allow reading beyond bounds, revealing credentials, keys, or user information stored nearby. Information disclosure is sometimes underestimated because it doesn't always produce an obvious crash or takeover, but it can be devastating because it can expose secrets that enable further compromise. For example, If an attacker can retrieve authentication tokens or cryptographic keys from memory, they may be able to impersonate users or decrypt protected content. Information disclosure also undermines many defenses because mitigations often rely on secrets, such as random memory layouts or hidden pointers. Once those secrets leak, the attacker's job becomes easier. Beginners should understand that memory safety vulnerabilities can be used to both steal data and enable deeper exploitation, and sometimes those two goals are combined in a single attack chain. Now let's talk about how these bugs become exploits, because understanding the exploit logic helps you see why mitigations matter. Exploitation often involves turning a memory safety flaw into control over a program's behavior. In a buffer overflow scenario, that might mean overwriting a value that influences where the program jumps next, or overwriting a pointer so that the program reads or executes attacker-chosen memory. In a use-after-free scenario, it might mean arranging for attacker-controlled data to occupy the freed memory so that when the program uses it, it behaves incorrectly in the attacker's favor. This is why attackers care about repeatability. A successful exploit must work reliably enough to be useful, not just crash occasionally. Modern exploit development often chains multiple steps, such as first triggering information disclosure to learn memory layout, and then using that knowledge to craft a precise corruption that yields code execution. The important beginner point is that exploitation is usually not magic. It is careful manipulation of program state through flaws in memory boundaries and lifecycle. Mitigations exist to break these steps, making exploitation unreliable or impossible. Mitigations for memory safety vulnerabilities aim to reduce the attacker's ability to turn a bug into a predictable exploit. One mitigation concept is making memory layout unpredictable, so attackers can't easily guess where important structures are in memory. Another mitigation concept is marking memory regions with permissions so code cannot be executed from places that should contain only data. There are also mitigations that add checks, such as detecting when memory has been corrupted or when a return address has been altered. Some mitigations reduce the risk of use after free by changing how freed memory is handled or by adding safety checks that detect invalid references. The common theme is that mitigations either prevent certain exploit techniques or make them too unreliable to be practical. For beginners, it helps to see mitigations as obstacles placed in the attacker's path, not as guarantees that no memory bug can ever be exploited. Attackers may bypass mitigations by finding additional bugs or by exploiting areas where mitigations are weaker. That is why mitigation is valuable, but not a substitute for fixing the bug. It's also important to recognize that mitigation coverage varies by platform and by configuration. Some systems have strong mitigation defaults and keep improving them over time, while others may have weak defaults or have features disabled for performance or compatibility reasons. Even within the same environment, different applications may be built with different security options, meaning one application benefits from modern mitigations and another does not. This variability explains why some vulnerabilities are catastrophic in one context, but less severe in another. It also explains why attackers often target widely deployed software with weak mitigation settings, because it offers reliable exploitation opportunities. For beginners, the main point is that modern systems try to reduce exploitability through built-in defenses, but those defenses are not uniform. Keeping systems updated matters not just for patches, but because updates often improve mitigation strength over time. A system that is years out of date may be missing entire classes of mitigation improvements. Now we can address why updates matter so much for memory safety vulnerabilities in particular. Many memory safety bugs are deep in code, hard to detect through normal observation, and can be exploited remotely, meaning an attacker might not need a user to click anything if the vulnerable component processes network traffic. When a vendor releases a patch, they are often responding to a real vulnerability that could be exploited, and sometimes the details of the fix reveal enough information for attackers to craft exploits quickly. This means patch timing is critical, because after a patch is released, attackers can compare versions and discover what changed, which can guide them to the vulnerability. That creates a dangerous period where unpatched systems are the easiest targets because defenders have not applied the fix, but attackers have learned where to aim. Beginners sometimes think patching is optional because exploitation sounds unlikely, But memory safety bugs in common libraries and services are among the most actively exploited vulnerability types precisely because they can be weaponized broadly. So updates are not just about getting new features. They are about removing known exploit paths from software that is constantly exposed to hostile input. Another reason updates matter is that memory safety bugs often appear in shared components that many applications depend on. If a vulnerability exists in a widely used library, it can affect browsers, servers, messaging clients, and embedded systems all at once, even if those applications are otherwise unrelated. This creates a scale effect where one bug can create risk across an entire ecosystem. It also makes patching challenging because organizations must patch not only the obvious application, but also the underlying components it uses, and they must do it consistently across many systems. Beginners sometimes assume that updating the operating system covers everything, but many vulnerabilities live at the application level or in bundled libraries that require separate updates. This is why asset awareness and patch management discipline matter so much. If you don't know where a component is used, you can't be sure you remove the vulnerability. Memory safety risk is therefore tied to software supply chain awareness, not just to local configuration. A practical way to think about defense is to combine 3 layers: reduce exposure, strengthen mitigations, and patch quickly. Reducing exposure means limiting what vulnerable services are reachable and limiting what content untrusted users can feed into sensitive components. Strengthening mitigations means using modern platforms and configurations that make exploitation harder, even when bugs exist. Patching quickly means removing known vulnerable code before it becomes an easy target. These layers reinforce each other because each one covers gaps in the others. If you can't patch instantly, exposure reduction and mitigations buy time. If exposure reduction is imperfect, patches and mitigations reduce the chance of successful exploitation. For beginners, this is a reassuring model because it shows you don't need a single perfect solution to be safer. You need a disciplined combination of controls that reduces attacker success probability. The deeper message is that memory safety risk is managed through routine engineering discipline, not through one special product. To close, memory safety vulnerabilities arise when programs mishandle memory boundaries or lifecycle, leading to overflows, use after free conditions, and information disclosure. Attackers exploit these flaws by turning memory corruption into control over program behavior, often chaining steps to make exploitation reliable. Mitigations exist to break exploit techniques by making memory unpredictable, enforcing execution rules, and detecting corruption, but mitigations vary across platforms and are not a substitute for fixing the underlying bug. Updates matter because patches remove known exploit paths, and because attackers can learn from patch changes, making unpatched systems especially vulnerable after fixes are released. Memory safety issues also matter because they often live in shared components, creating wide blast radius across many applications. When you combine reduced exposure, strong mitigations, and disciplined patching, you create a systematic defense that makes memory-based exploitation harder, noisier, and less reliable. That is why memory safety and updates are not just developer concerns. They are foundational security concerns for anyone responsible for keeping systems trustworthy.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.